Stars can sometimes reach colossal sizes comparable to entire solar systems. The more massive a star, say 10,000 times the mass of our Sun, the faster it must burn through its nuclear fuel to counteract the relentless pull of gravity. Consequently, the lifespans of such stellar giants are remarkably short on cosmic timescales. While the exact parameters of the largest known star remain a topic of scientific debate, one of the most impressive and easily visible to the naked eye is Betelgeuse, located in the constellation Orion. Remarkably, if Betelgeuse were placed at the center of our solar system, its outer layers would extend nearly to, or possibly even beyond, Jupiter's orbit, meaning Jupiter would orbit inside the star itself. Its sheer scale is so immense that even Earth-based telescopes can resolve features like star spots on its surface. Betelgeuse is a star in the final stages of its life, having swollen to an extraordinary size. Yet, it is not the largest known. Our observational reach extends so far into the cosmos that we can detect light emitted just 380,000 years after the Big Bang, the moment the universe became transparent. Embedded within this primordial light, which predates the formation of stars and galaxies, are patterns that strikingly mirror the large-scale distribution of galaxies we observe across the sky today. Where did these initial structures originate? The most compelling explanation is the theory of cosmic inflation. It proposes that before the hot, dense state we call the Big Bang, the universe already existed, as a cold, nearly empty space undergoing exponential expansion. This rapid inflationary phase eventually ended, slowing down and converting its energy into heat, thereby producing the particles that would later coalesce into stars and galaxies. This process is known as inflation, and Mars stands out as the only planet beyond Earth that humanity could realistically colonize. It is relatively accessible and hospitable for settlement. Vast quantities of water lie beneath its surface or are frozen in its polar ice caps, facts we are confident about. Mars also contains all the essential minerals needed to build a civilization. We already possess the technology to extract this water and split it into oxygen and hydrogen, critical for breathable air, rocket fuel, and electricity, forming the foundation of a new society. The question is not whether we can do it, but whether we have the will and when we will act. Most Mars mission plans envision sending robotic systems ahead of human crews to construct a base, akin to building a house before moving in. This approach appears to be the most viable path forward. Does Mars require terraforming? Terraforming, deliberately altering a planet's atmosphere, is a long-term objective, but one we believe is fundamentally achievable. Consider Hellas Planitia, a region on Mars almost certainly a massive impact basin. Its depth reaches about 9 kilometers below the planetary datum. So vast is this depression that if Mount Everest were placed at its lowest point, its peak would still be visible from the rim. The atmospheric pressure at the basin's floor is high enough that liquid water could occasionally exist there today, despite Mars's generally thin atmosphere. This suggests that only modest atmospheric modifications are needed. Introducing greenhouse gases like carbon dioxide could thicken the atmosphere, raise temperatures, and enable plant life. With water already present, photosynthesis could gradually generate oxygen, potentially restoring a breathable atmosphere. Could humanity ever use wormholes for time travel? This remains one of the deepest questions in theoretical physics. Can such structures exist at all? 2. Einstein's theory of general relativity permits them mathematically. However, their stability is highly questionable. Would they collapse the moment anything, even a single photon, tried to pass through? Most physicists believe that while wormholes might theoretically exist, they would be extraordinarily unstable, collapsing instantly before any information or matter could traverse them. Thus, using them as time machines to visit the past seems implausible. A definitive answer, however, awaits a complete theory of quantum gravity. How did the moon form? The prevailing theory holds that it resulted from a cataclysmic collision early in the solar system's history, roughly 4.5 billion years ago. A Mars-sized protoplanet struck the young Earth in a glancing blow, ejecting a vast cloud of debris into orbit. This material briefly formed a ring around Earth, similar to Saturn's rings, before rapidly coalescing into the Moon. Consequently, the Moon is composed mostly of material from Earth's mantle, mixed with fragments of the impacting body. This event occurred very soon after Earth itself formed. Could a spacecraft fly through Jupiter, the gas giant? The answer is a clear no. While its upper atmosphere is diffuse enough to allow passage, conditions grow increasingly extreme toward the core. Immense pressures and temperatures, reaching tens of thousands of degrees, await any probe. Scientists believe Jupiter's interior may contain exotic states of matter, such as metallic liquid hydrogen. NASA's Juno mission is currently studying Jupiter to uncover secrets of its deep interior. But any attempt to reach the core would result in the spacecraft being crushed, melted, and likely destroyed upon encountering dense. What about the multiverse? While no direct evidence exists, several theoretical models propose its reality. One of the most compelling to physicists is the inflationary multiverse. Observations show that galaxies are not randomly scattered, but exhibit subtle patterns, clustering along circular distributions that trace back to the oldest light in the universe, the cosmic microwave background. Inflationary theory suggests that the rapid expansion of space did not end everywhere at once. Instead, localized regions dropped out of inflation, each triggering its own Big Bang and forming a separate universe. Meanwhile, the greater multiverse continues inflating, spawning countless bubble universes. Our entire observable cosmos, with its estimated 2 trillion galaxies, may be just one such bubble. Why do some planets like Earth and Jupiter have magnetic fields, while others like Mars and Venus do not? Mars, being significantly smaller than Earth, has a higher surface area to volume ratio, a principle also seen in nature, where small animals like mice lose body heat faster than larger ones. All planets form from colliding rocky bodies, generating internal heat from both accretion and radioactive decay. Smaller planets radiate this heat into space more efficiently due to their larger relative surface area. As a result, Mars, core cooled and solidified over time, halting the convective motion of molten iron necessary to generate a global magnetic field, leading to its eventual loss. Why is the night sky dark despite the billions of stars in the universe? This is Olber's paradox. If the universe were infinite, static, and eternal, every line of sight should eventually end on a star, making the entire sky as bright as the sun's surface. The fact that the night sky is dark tells us the universe is neither infinite nor eternal in the classical sense. Instead, it is expanding and has a finite age. Light from stars beyond a certain distance hasn't had time to reach us, and the expansion of space redshifts distant light out of the visible spectrum. These factors together explain the darkness of the night sky. How can light behave both as a particle and a wave? In particle physics experiments, photons and other quantum entities often act like tiny billiard balls, colliding, scattering, and carrying momentum, even if massless. Yet, to predict their behavior, we use mathematical frameworks rooted in wave mechanics. For instance, interference patterns, where wave peaks and troughs cancel or reinforce, emerge even when single particles are sent through experiments one at a time. This suggests that while particles remain discrete entities, their motion is governed by wave-like probabilities. They don't follow classical trajectories. Instead, their possible paths interfere like waves. Thus, it's most accurate to say particles are particles, but their dynamics defy everyday intuition and are described by wave mathematics. Einstein's theory of general relativity, remarkably, predicts its own limitations. It implies that at the center of a black hole or a collapsing star, space-time curvature becomes infinite, a singularity. Yet physicists strongly suspect this is unphysical. One key reason is Stephen Hawking's discovery that black holes are not eternal. Through quantum effects near the event horizon, they emit radiation, now called Hawking radiation, slowly losing mass and energy over time. Hawking realized that quantum mechanics dictates that empty space is never truly empty. Virtual particle-antiparticle pairs constantly flicker in and out of existence, borrowing energy from the vacuum briefly, in accordance with the energy-time uncertainty principle. Near a black hole's event horizon, one particle of the escaped particle becomes real, carrying energy away from the black hole. Thus, the black hole radiates, has a temperature, and eventually evaporates. This shows that time doesn't end inside a black hole. The singularity is a sign that general relativity breaks down, not that reality does. Quantum gravity must resolve these infinities. The same applies to the Big Bang singularity. While we know a more complete theory must exist, we have not yet formulated it. Hawking radiation, however, represents a crucial first step toward unifying quantum mechanics and gravity. Particle physics is, at its core, a game of statistics. It's akin to flipping a coin 100 times. You might very well get 99 heads. That doesn't mean the coin is rigged. Such an outcome, however improbable, is still possible. At the Large Hadron Collider, LHC, around 600 million collisions occur every second, or even more, generating an enormous number of interactions and a colossal volume of data. Consequently, phenomena often appear that initially seem like new particles, but typically vanish as more data accumulates. These are statistical fluctuations. However, we have occasionally seen hints in older data that strongly resemble new particles, and we need fresh data to determine whether these signals fade away or persist. One famous example is the so-called diphoton excess at a mass of approximately 750 proton masses, far heavier than the Higgs boson, which weighs in at about 120 proton masses. This hypothetical particle would have decayed into 2 photons, but its nature remained a mystery. Over 200 theoretical papers were published, each proposing a different explanation. In short, no one knew what it was, even whether it truly existed. If such a signal were to persist, one compelling hypothesis is that it could. The idea of extra dimensions dates back to the 1930s with the Kaluza-Klein graviton hypothesis, which suggested the existence of spatial dimensions so tightly curled up that they remain invisible to us. A common analogy compares this to a garden hose. From afar it looks like a one-dimensional line, but up close it's clearly a cylinder with a second circular dimension. Similarly, our universe might harbor hidden spatial dimensions. One potential signature of their existence would be towers of heavy particles, analogous to the harmonics on a guitar string. If we ever detect such patterns, it could open a window into the physics of extra dimensions, and perhaps even help unify gravity with the other fundamental forces. While many such signals disappear with more data, the possibility of a genuine discovery keeps the field thrilling. In cosmology, our understanding of the universe is built upon multiple independent measurements that must converge into a coherent picture. For instance, the age of the Earth is determined through radiometric dating, a highly precise technique that measures the decay of radioactive isotopes in rocks. The oldest terrestrial rocks and meteorites consistently point to an age of about 4 billion years. Turning to the Sun, helioseismology, the study of solar oscillations or sunquakes, allows us to probe its interior. By analyzing these vibrations, we can measure the amount of helium in the Sun's core. Knowing that the Sun shines by fusing hydrogen into helium, and given its observed luminosity,
We can calculate the rate of nuclear reactions and thus infer its age, roughly 4.7 billion years. These entirely different methods yield consistent results, reinforcing our cosmological model.
In the 1990s, measurements of the universe expansion rate suggested an age of only 11 to 12 billion years. Yet, the oldest globular clusters in the Milky Way appear to be about 12 billion years old. This paradox implied the universe was younger than its oldest stars. The puzzle was resolved in 1998 when Brian Schmidt and another team in the US, observing distant supernovae, found them dimmer than expected. This led to the revolutionary conclusion that the universe's expansion is accelerating, a shock since it was previously assumed to be slowing down. This discovery revised the estimated age of the universe to 13.8 billion years. It's precisely this commitment to data, even when it contradicts expectations, and the willingness to keep measuring that gradually refine our cosmic worldview, where consistency across diverse observations is paramount. Why is the speed of light finite rather than infinite? The simple answer is that's just how the universe is. But Einstein's theory offers a deeper insight. The finite speed of light is woven into the very geometry of space-time. It defines that geometry. 2.0. Einstein's relativity, grounded in experimental evidence, treats space and time as a unified continuum. We can move freely through space, but not through time. We cannot return to the past or halt our progression into the future, though we can alter our rate of travel into the future relative to others. This asymmetry between time and space arises from a universal speed that all observers agree on, an invariant in the theory. Moreover, the term speed of light can be misleading. Light travels at this speed only because photons are massless. In reality, it's massless entities that must move at this speed, while massive objects cannot reach or exceed it. This universal speed for massless particles shapes spacetime's geometry, prevents time travel to the past, and gives rise to the famous equation, why is c squared the conversion factor between mass and energy? Because it's tied to the behavior of massless entities. Thus, light moving at the speed of light is, in a sense, a coincidence. The idea of an eternal universe remains speculative and hotly debated. Stephen Hawking and James Hartle once proposed a theorem stating that any eternally expanding universe must have had a beginning in time. Yet some physicists are actively seeking ways around this conclusion, reflecting the dynamic nature of cosmology. If future observations confirm that the universe is eternal, and our Big Bang 13.8 billion years ago was merely the start of one region within a larger structure, it would open profound new questions. What existed before the Big Bang? How long had that prior state lasted? Was it eternal? Is its existence logically necessary? These questions lie at the frontier of current research, with no definitive answers yet, but perhaps answers will emerge soon. Meanwhile, the search for life beyond Earth is gaining momentum. Conditions on Mars, such as subsurface liquid water and geological activity, appear potentially habitable. Similar environments may exist on Saturn's moon Enceladus and Jupiter's moon Europa. Even Pluto is thought to harbor geological activity and vast amounts of water ice, possibly with a subsurface ocean. The most promising near-term effort is the ExoMars mission, a joint European-Russian project. An orbiter is already in place, and a rover designed to explore the surface will soon begin its work. Within our lifetimes, we may discover microbial life that arose independently elsewhere in the solar system. Equally exciting is our growing ability not only to detect exoplanets, over 2,000 have been confirmed, but also to analyze their atmospheres. Water vapor has already been found in the atmospheres of some large gas giants, though life is unlikely there. Soon, a key biosignature would be abundant atmospheric oxygen, as oxygen-rich atmospheres are unstable without continuous replenishment, on Earth via photosynthesis. No known geological process can maintain 20% oxygen levels over geological timescales. Even more speculative are searches for industrial pollutants like chlorofluorocarbons in exoplanet atmospheres. Within the next 2 decades, our technology will likely allow us to probe the atmospheres of rocky exoplanets in detail. It's entirely possible that we discover life beyond our solar system, not by seeing organisms directly, but through their chemical fingerprints in alien skies.